In this video, we're going to look at some notes on normal distributions. So first, we just described what a normal curve was. So let's go back over what are the characteristics of a normal curve. So first of all, with a normal curve, the mean, the median, and the mode all have to be equal. So our three measures of central tendency have to be the same thing. Second, if it's symmetrical, and it has to be bell-shaped. It has to be both symmetrical and bell-shaped. Third, the total area under the curve has to be 1 because that's the sum of all the probabilities. And the last one, the curve doesn't touch the x-axis, but it gets closer the further it is from the mean. So a normal shaped curve, they're all going to look like this. They're all going to flatten out, make the bell shape, and come back down. Right here in the middle, we're going to have the mean, the median, and the mode all in the same place. If I shaded in all of this, that area would have to equal 1, and that's the sum of all the probabilities of everything happening. And then again, with that bell shape, it tapers out on the ends, and that's why it gets closer to the x-axis. So those are some characteristics of a normal curve. If you still need time to write them down, you can pause the video. All right, some examples of things that would be normal distributions. LDL level cholesterols in adults. Most people are average, some people are higher, some people are lower. IQ scores, again, same type of thing. SAT and ACT scores, definitely this bell-shaped normal curve. The width of stripes on a zebra. The acidity of rainfall in the Shenandoah Mountains. The length of time it takes milk to spoil. The size of eggs produced by young hens. All of these things would make nice normal distributions. A good rule of thumb, nature loves normal. What is another example that you can think of? Well, there's tons of them. An example that I had from the past was the height of people's foot arches. People's weights. Oops. That says people's weights. Anything that happens in nature like this is oftentimes a normal distribution. All of these things would cover the 4 characteristics that we had up here on the top. All right, so what can make normal curves different? Well, depending on what the average is, since the average is in the middle, we could say the location of the curve on the x-axis okay. So for instance, if I were going to do the average weight of people all over the world, I might get this bell-shaped curve. Then if I were going to do the weight of people in a 4th grade class, well, maybe that one would be down here to the left because the average would be lower. But in order to keep that having the same area, so in order to take this curve here and to have it make the same area underneath being 1, if I'm going to make my curve skinnier, I'm also going to have to make it taller. Oh, my graph's not letting me get taller all of a sudden. So if my average were going to be lower, I could have a tall, skinny normal curve, or I could have a shorter, fatter normal curve. So I could have the location of the curve on the x-axis and then also the height and width. So I could be tall and skinny, or I could be short and fat, but the area underneath has to be the same. So because we have all these different normal curves and they could be all over the place, in math they decided to make a standard normal curve, and that's what we have down here at the bottom. The standard normal curve has mu equal to 0. That means the mean is equal to 0, and that's shown right here in the middle. This 0 is the average. Okay, it's also the mean and the median and the mode, all of them. All right, and the standard deviation, which is the lowercase sigma, is 1. So that means if I go out, my average spread of my data is 1 unit. So this is considered 1 standard deviation out. Over here, we'd have 2 standard deviations out. Over here, 3 standard deviations. This would be 1 standard deviation to the left, 2 standard deviations to the left, and 3 standard deviations to the left. So typically when we make a graph, we're going to mark the mean in the middle, and then we're going to go out 3 standard deviations in each direction. We're going to make them positive going to the right, and we're going to make them negative going to the left, but we're going to go 3 standard deviations in each direction of the mean when we mark our graph. So let's turn the page and see how we can actually do this. So if we have a normal distribution, there's what we call the empirical rule. The empirical rule also has the name the 68, 95, 99.7 rule. And that's something you really want to memorize. We know those numbers, 68, 95, 99.7. You'll use them a lot. So what does this mean? What is this rule? This says in a normal distribution, 68% of the total data lies within 1 standard deviation of the mean. So this is 1 standard deviation below. This is 1 standard deviation above the mean. So if I looked at everybody who fell within this range right here, that would cover 68% of all the people, or of all the foot arches, or of all the eggs, whatever it is you're talking about. Okay, the next number in the rule is 95. 95% of the normal distribution lies within 2 standard deviations of the mean. So if I went out 2 standard deviations in each direction, 2 up and 2 down, this part right here will cover 95% of all people, or of all pieces of data. 99.7, that's almost everything. 99.7% of the data lies within 3 standard deviations of the mean. So if I go out 3 standard deviations in each direction, all I'm missing is a tiny little tail in each direction. So the only part that's not shaded are these little bits down here on the end. The part that is shaded would be 99.7% of all the data. So this is our rule that tells us how much is in each section of the normal distribution. So if we were to break it down into parts, we have the 68, 95, 99.7% rule. So this tells me that 68% of our data is right here. If I have to divide that 68% into these 2 strips, this first strip on the left here is 34% of the data, and the strip on the right is 34% of the data. Put them together, that makes 68. The next number was 95. So that means right here, this is 95% of the data. However, if I'm trying to figure out how much is in this strip versus this strip over here, I have to account for the fact that out of that 95%, I've already taken out 68%. So what I have left is 27%, and then I've got to take that 27%, and then I've got to take half of it. So half of 27% is 13.5%, and that's how much is in each of these strips, 13.5% and 13.5%. Then I moved down to my last number, which was 99.7%. So right here, through 3 standard deviations, I had 99.7%. But I've got to get rid of the 95% that I already had in there. So that leaves me with 4.7% between the 2 strips. And then I'm going to take half of the 4.7, which gives me 2.35%. And each of these little bits right here is 2.35%. So how much is left? Well, I had a total of 100%. I took away 99.7% of the data so far, so that leaves me with 0.3%. to then divide by 2, and that's 0.15%. So in each of these little tails on the end here, I just have 0.15% of all of my data in that little end. Okay, so we need to understand how to calculate any of these. We need to know that 68, 95, 99.7% rule. But in reality, what do they mean? What does it mean to say something's normal? What does it mean if you're within one standard deviation of the mean? Let's take this to something we can visualize. And if you turn the page, we talk about the men's heights. So in this normal curve, we've taken the heights of 1,000 American men and we've measured them. The mean or the average height was 5 foot 9 inches. We would show that by saying mu equals 5 foot 9 inches. And the standard deviation is 3 inches. I'd show that by saying sigma is 3 inches. So if I were to put that on this graph, right here, my mean, my middle, has to be at 5 foot 9 inches. Then each little mark for my standard deviations is going to go out 3 inches. So if I take 5 foot 9 and I add 3 inches to it, that puts me at 6 feet tall. If I add 3 more inches, that puts me at 6 foot 3 inches tall. Whoops, I wrote 6'6", I said 6'3". Okay, so that puts me at 6 foot 3 inches tall. If I add another 3 inches, that puts me at 6 foot 6 inches tall. And then this is going off to forever. Let's work down now. If I went 3 inches under to go less than the mean, that would be at 5 foot 6 inches. If I went down another 3 inches, I would be at 5 foot 3 inches tall. If I went down another 3 inches, I would be at 5 feet tall, and then I could go forever in the short direction. All right, so what does this mean? It says label the horizontal axis with the heights that each tick mark represents. That's what we just did. What is the probability that a man chosen is over 5 foot 9 inches? On each of these things, what we're going to do is we're going to look and say, where is this? 5'9" is right here in the middle, 5 foot 9 inches. Decimal. What is the probability that a man chosen is over 5'9"? So that means he have to be over here on the right side of the graph. How many people are above the mean? Half of the people are above the mean. So the probability would be 0.5 or 1/2. What is the percentage of men that are over 5 foot 9 inches? Again, the same area, but in this case we want a percentage, so half is 50%. How many men are expected to be above 5 foot 9 inches tall? Well, there were 1,000 men in the original sample, and then we had to take half of them, so that would be 500 men. All three of these things really ask the same question. It asked who was over here on the right side of the graph. You just have to be sure you're answering in the units they're asking for. A probability is a little number, like a fraction or a decimal. A percentage is a percent, and how many men are expected would be an actual number of men. By the way, if this number had turned out to be a decimal, I would probably round it because we can't have a portion of a person. So before we go on to the rest of these questions, let's just look at our initial picture up here at the top for a second. What does it mean to be within one standard deviation of the mean? To be within one standard deviation of the mean is 68% of people. So what we're saying is 68% of men are between 5 foot 6 inches tall and 6 foot tall. Okay, this is what we consider normal. If a guy walked into the room right now and he was 5 foot 8, we think he looks pretty normal. If a guy walked in and he was 6 feet tall, that's not abnormal. It's pretty normal. 5 foot 6 to 6 foot tall is pretty much your average type of height. Then we go out to 2 standard deviations. So now we're in this zone. That's the 95%. 68, 95, 99.7. So 95% of men are between 5 foot 3 inches tall and 6 foot 3 inches tall. So if a guy walked into the room and he was 6 foot 2, so he'd be over here. If he's 6 foot 2, you might think he's a little tall. If a guy walked in and he's an adult and he's 5'4", you might think, he's a little short, but it wouldn't be really that remarkable. He still falls in the pretty typical range. Then we get out into our 99.7. So 99.7, now I'm within 3 standard deviations. Almost everybody is falling within 3 standard deviations. So 99.7% of men are between 5 feet tall and 6 foot 6 inches. So if a guy walked into the room and he's 6'5", you're going to say, oh, he's tall. Okay, and you're going to notice that type of thing. The last area on our picture is this little end out here, these little tails, and these are really the extremes. That's 3.3% of the population. If a guy walks in and he's 6'8" tall, everybody in the room is going to notice, wow, that guy is tall. Or if a guy walks in and he's 4'8", you're going to notice he's short. And we can all sort of make this assumption of where people fall with what is considered the middle or average versus far off from average. So keep those things in mind when you're trying to answer the questions. Okay, so let's move down here. So what percentage of men are between 5'6" and 6'0"? So where were those marks? 5'6" was right here at 1 standard deviation away. 6'0" was over here at 1 standard deviation away. So that was this strip down the middle, and that was, 68% of people fall within 1 standard deviation of the mean. So what is the probability that a person chosen at random is between 5'6" and 6'3"? So 5'6", that was right here. That was our 1 standard deviation. Then we had 6 foot. Then we had 6'3". So now I've got to take my original chunk that I had here, and then I'm going to add 1 more standard deviation for just this above the mean part. So what is the probability? Well, the probability of being in this blue region right here is 0.68, because that was the 68% of the people. Then if you flip back, when we found the area of each of these strips, we found those strips were each 13.5%, or 0.135 as a decimal. So if I'm going to find the probability that I'm within both of these regions put together, I would have to add those 2 numbers. So 0.68 plus 0.135 is 0.815, which is also 81.5%, but it asked for a probability, so I'm going to give that as a decimal. Number 7 deals with the same range between 5'6" and 6'3", and it asks how many men are expected to be there. So if we have this 0.815 times the 1,000 men that I originally chose in my survey, that would be 815 men. All right. Question number 8 says, what is the probability that a man chosen at random is less than 5'6" or over 6'3"? So we're taking our same interval that we just had up here, except for instead of choosing the people between those values, we're choosing that they are less than 5'6", so I'm over here on the left, or over 6'3", so I'm over here on the right. Well, I know that my total probability is 1 for the area under there. If I then subtract the 0.815, which was the probability that I was inside that region, I get 0.185 is the difference. So I took away what I learned in number 6. Number 9 says how many men are expected to be under 5'6". So 5'6" again was this 1 standard deviation under the mean. How many men are expected to be under 5'6"? I can tell from my picture that this is going to be less than half. It's not going to be a huge number. So I need to figure out how many people are over here. Well, if I did the 1 standard deviation within the mean, I knew that 68% of the people were here, which means if I have 100% people total minus 68% of the people, I'm going to have 32% that are outside in these two ends. But I only want one of those ends, so I'm going to take half of that 32%, and that's 16%, or 0.16 is a decimal. So the probability that I'm over here is 0.016. How many men does that equal? Well, I'd take my 1,000 men times 0.16, and that gives me 160 men. The last way that we'll describe people is with this word right here, percentile. And your percentile means what percent of people are at or below you. So right here, when I got that this probability was 0.16 or 16%, that means you're in the 16th percentile because you are as tall as 16% of the people. Sometimes it's a good thing to be in a low percentile, other times it's a good thing to be in a high percentile. But this means that you are at least as tall as 16% of people. Okay, so we need to memorize this 68, 95, 99.7% rule, and we need to be able to go back to what we had down here and break apart and realize how big each of these percents were. So you either have to have them memorized or you have to be able to figure them out quickly by doing addition, subtraction, and division. All right, come into class and we'll do some practice problems with more of this information.